Which of the following triangles are similar to triangle ABC? So let's just review what similarity means when we're talking about triangles. So let's say this is one triangle, and I'll assume it's a right triangle, although what I'm about to say is true for any triangle. And let's say this is another one. You have similar triangles if all of the corresponding angles are equivalent. So that angle is equivalent to that angle, and I drew that as a right angle. Let's say that this angle is equivalent to this angle, and let's say that this angle is equivalent to that angle. Then these two triangles are similar. They are not necessarily congruent. They don't necessarily have all of the same sides. But when you have, they do have all of the same angles, and when you have all of the same angles, the ratios between corresponding sides is going to be constant. So for example, if this side has length 2 and this side has length 1, you have a 2-to-1 ratio between the second longest side and the shortest side, then you're also going to have a 2-to-1 ratio here. So maybe this has length 3, then this one would be 1.5. 3 to 1.5 is the same thing as 2 to 1. Now, let's think about the triangles that they are proposing. So the first one is triangle CDE. So C, D, C, D, E. Just like triangle ABC, this is going to be a right triangle. This is going to be a right triangle. How do I know? Well, side CB is perfectly horizontal and side AB is perfectly vertical. Same thing. Side DE is perfectly horizontal and side CE is perfectly vertical. Now, you might realize that you have the same line acting as a hypotenuse of both of these triangles. So you have the same line right over here. And if we wanted to prove that the corresponding angles are equivalent, we just have to break out a little bit of our geometry. We see that we have these two vertical lines. So CE, this line segment CE, you could view it as part of a larger line that goes like this. It is parallel to AB. It is parallel to AB. So if you view these as two parallel lines, so that is parallel to this, then, and you have a transversal right over here, then corresponding angles are going to be equivalent. So this angle right over here is going to be equivalent to that angle right over there. Similarly, I have trouble saying that word, segment DE right over here is parallel to BC. And so if you once again look at the blue line as a transversal, this angle is going to be equivalent to that angle. So all of their corresponding angles are equivalent. So these are definitely similar triangles. Now, I went through that fairly long-winded geometry way of thinking about it, but there's an easier way to think about it. Anytime you have a line and you construct a right angle where essentially a right triangle where the base of the right triangle is essentially your change in x between these 2 points. So if you think about going from point C to point A, and if you first just wanted to have a change in x, so this is our change in x right over there, and then you have a change in y, and then you have a change in y, so this is our change in y, you're going to construct a right triangle, and the ratio between these two sides is always going to be the same. So delta y, the change in y, this triangle, this is the Greek letter delta, just a shorthand for saying change in y, which is the length of this side, over your change in x, is always going to be constant when you are dealing with a line. So any triangle that's constructed this way from this line, the ratio between the corresponding sides are going to be equivalent, and they're going to be similar triangles. So that would have been an easier way to think about this right over here. Now let's look at the other options they give us. DFG. DFG. So that's DFG. Well, there's not really a lot that we can say about DFG. We're not really using the line anymore as a hypotenuse, so we're not going to throw that in there as being similar. We could actually look at the lengths and all of that if we wanted, but we'd see that it's not similar. CDG. CDG. Well, once again, this is not, CDG, clean this up a little bit. CDG I'll do in, let's see, I'll do in blue. So CDG, this is not a right triangle. This isn't just a change in x right over here. This isn't a horizontal line. And this one right over here is not a vertical line. So once again, this is not similar. In fact, this is not even a right triangle. So we'll mark both of these out. And then they say ADF. So ADF. Well, once again, ADF, it's a right triangle. It's a right triangle between D and F. You're essentially, it's your change in x going from D, so D is at -2, A is at 3. This right over here is your change in x. You literally had to go 5. This length right over here is 5. And then this right over here is now vertical line. This is a right triangle. This is your change in y. So that is your change in y. And these two ratios are always going to be constant when your hypotenuse is a line. So once again, this is just one of those classic right triangles constructed from the line where the base is the change in x, this height is the change in y, the hypotenuse is the line itself. These are going to be similar. So this is definitely a similar triangle. And now let's actually input it just to make sure that we got the right answer. So I'm saying that and that are right triangles, or sorry, that they're similar triangles to triangle ABC.